Welcome to another podcast. In this episode, we're going to be taking a look at another Laplace transform. This one's a little bit more difficult to pin down than cosine and sine and the exponentials that we looked at previously. Let's just remind ourselves what the Laplace transform formula is here. So the Laplace transform of the function f of t is defined to be the integral from 0 to infinity of f of t e to the minus st dt, and that integral is a function of a frequency variable s. Now, for this particular problem, I'm interested in looking at what happens when I try to take the Laplace transform of t raised to a power. In other words, we're looking at power functions. Because of the linearity of the Laplace transform, if I'm able to get this formula, if I'm able to come up with the transform pair for t to the n, then I'll automatically be able to take the Laplace transform of any polynomial because it's just a linear combination of power functions. So going straight off the definition here, the Laplace transform of t to the n would be the integral from 0 to infinity of t to the n e to the minus st dt. And immediately we see that we're going to have to do integration by parts. We pretty much have no option here. So remember how integration by parts works. You pick your u, which is going to be t to the n, and we pick a dv, which is going to, in this case, be e to the minus st dt. So my u is t to the n, so my du is n t to the n minus 1. dv is e to the minus st dt, and you got to be careful here. The integral, or the antiderivative of that, is e to the minus st over negative s. And so this is the integration by parts substitution. And when I make that substitution into the integral, I have t to the n e to the minus st over negative s. This is the u times v part. Remember, because this is a definite integral, even though it's improper, I still have to evaluate it from 0 to infinity. And then the next piece would be v du, which would be minus, but remember it's a negative already, so this is going to be plus. The integral from 0 to infinity of v du would be n t to the n minus 1 e to the minus st over s, and I'm going to stick the s here with the n since they're both constants in this case. S is not technically a constant, it's just constant with respect to the variable of integration, which is t. So let's begin by talking about this first piece. If I try to plug in infinity, then, so maybe off to the side here, if we just look at this, the limit as t goes to infinity of t to the n e to the minus st over negative s. If I look at that, then since s is greater than 0, this is t going to infinity in the denominator, which would be, in this case, we'd have 0, and t going to infinity in the top, this piece would go to infinity. So what we have is this piece going to infinity, this piece going to 0. So this is a indeterminate form of type infinity over 0 in this case. Because it's indeterminate, if I want to try to find its limit, I need to use L'Hopital's rule. Alright, so I want to think of using L'Hopital's rule on this, and the idea is I would be looking at the limit as t goes to infinity of, and I need to have it in the form infinity over 0, so the best way to do that is keep the t to the n in the top, and then we would have minus s e to the, well, when you bring e to the minus st down, it's e to the st down here. And if I try to look at that limit and I start taking derivatives, then L'Hopital's rule says that I keep taking derivatives of the top and derivatives of the bottom. Eventually I'll run out of powers, but no matter how many times I take the derivative of e to the st, it's going to remain in the bottom. So eventually, after n applications of L'Hopital's rule, I'll end up with a n factorial, because I'll get the power n to come down each time. And then on the bottom, I'll have copies of s. I'll end up with minus s to the n plus 1 e to the st, and that limit as t goes to infinity is going to be 0. So the nice thing is we get 0 from evaluating it at the infinite limit, and we get 0 from evaluating it at 0. So this part does not contribute. This is a really good application of L'Hopital's rule, so you want to make sure that you kind of understand where all that came from. Now, for this particular problem, looking at the second piece of the integral here, n over s is a constant with respect to the variable of integration, so I'm going to pull it outside the integral. And I'm looking at the integral from 0 to infinity of t to the n minus 1 e to the minus st dt. So I want to show you what happened here. We took the Laplace transform of t to the n, which looks like this, and instead we have an integral that's t to the n minus 1. We managed to reduce the power of the function by 1. So another way to write this is that this is n over s, the Laplace transform now of t to the n minus 1. So this gives me a way of reducing, this is sort of a reduction formula, a way of reducing the power of a function. And if I do this multiple times, then the Laplace transform of t to the n is n over s, Laplace transform of t to the n minus 1. Do it again, I would get an n squared over, or excuse me, not an n squared, an n minus 1, because it would now be a power n minus 1 coming out. I would get another copy of s, so it would be s squared, and it would be the Laplace transform of t to the n minus 2. Eventually, this process is going to play out where I finally have a t to the 1 and I bring it out. At that point, I would have n copies of s, and I would be left with the Laplace transform of t to the 0, which is the same thing as n factorial over s to the n. Laplace transform of t to the 0 is 1. And we know from previous work that 1 has a Laplace transform of 1 over s. And so our final answer here is this is n factorial over s to the n plus 1. So maybe just provide a small example of this. What is the Laplace transform of 3? Let's do t to the 5th. Well, based on the formula, this is the same thing as 3 times the Laplace transform of t to the 5th. And the formula says that t to the 5th, so n would be 5 in this case, would be 5 factorial over s to the 5 plus 1, or s to the 6th. And so that would be the Laplace transform. 5 factorial is 120 times 3 is 360, so 360 over s to the 6th would be the Laplace transform of that function. Now, in the next video, we're actually going to look at an alternative form of this particular transform. This transform is important because it has two different forms. And so what you'll notice here is that this description of the transform is only good for certain values of n. In other words, what if my power is n equal to 1/2? What do I do then? That certainly makes sense, right? N equal to 1/2 would just be the square root of t. I might want to know what the Laplace transform is for that. But I certainly don't know, at least right now, what the factorial is for 1/2. What is 1/2 factorial? What does that even mean? And so in the next video, we're actually going to take a look at that. All right, thank you for watching.